वो उस पे लाइव यूट्यूब लाइव। Okay. So, good morning, everyone. So, earlier, basically, you had a lecture on risk management, how to basically handle the risk. There, I think you must have, uh, discussed about good morning, about like contact for differences, bilateral contacts, and different risk handling like forward options and also different techniques you must have studied there. Today, we will talk about renewable self scheduling, that how renewable scheduling is done. Okay. And what should be the objective of a renewable company. Okay. And as renewable is uncertain, so we should basically like how to handle the risk as well. So those kind of modelings we will going to discuss today. Can you push please open the chat window there? Thank you. So I will share my screen with you. So today, basically, we will talk about the renewable self-scheduling. As we know, renewable is basically very much uncertain, and uncertainty basically leads to risk in decision making. Okay, so anyone wants to make some decision, if information is not certain, or we basically don't know about certain information, whatever decision we are making, it will involve certain risk. Okay. So, what can be the sources? What can be the sources of uncertainty? Very first is like if you are doing some planning, or let's say too much advanced analysis, then availability of certain units, we can say, and network as well. Like some network is, let's say, line is out for maintenance, and also that information. So for maintenance, I will not call it uncertain because it is scheduled, but some unexpected line outage or unit outage will leads to basically uncertainty whether that unit is will be available or not. Apart from that, we are very much know that all renewable supply, whether it is your wind or let's say solar, basically they are uncertain in the nature. They are weather dependent, so they are uncertain, that we don't know how much we are going to produce. So any, like, you cannot say that tomorrow this much quantity will be produced by wind power plant at a particular time period. So that is uncertain. Then market prices are also driven by the supply demand balance. So market prices are also uncertain, and then demand is also uncertain. Okay, so demand is also weather dependent. So demand is also not constant, and you cannot predict it. So based upon the like generation, our renewable is uncertain, demand is uncertain. So market price is outcome of basically supply and demand balance. So if supply and demand is uncertain, your prices will also be uncertain. So these are the, like few sources of uncertainty in power system operation. Now, if I just talk about from a demand point of view, what will happen that so you we can predict, like some forecasting techniques we can use, and based using those forecasting techniques, we can predict that okay, this will be the demand, or this will be the a renewable generation. Based upon that, we can predict either solar power. So there are many, um, people are working on solar or wind power, basically forecasting, load forecasting, which is forecasting the demand, and your price forecasting as well. So certain scenarios are there, certain trends are there, and based upon those trends, different techniques are there to forecast the market price, demand, and your generation. So we have a certain idea that okay, this is and these forecasts are also depending upon like how much ahead we are doing the forecast. They will have a certain accuracy. So if let's say I am doing a forecast year ahead, it will have very less accuracy because we don't know what will happen after a year. But still, we can forecast it, and the accuracy of that forecast will be less as compared to, let's say, I want to predict what will happen in the next hour. So what will be the wind production or demand? Then it is easier to forecast. So based upon so we have different forecasts, short term forecast, even very short term, long term forecast. Based upon those forecasts, system operate from the system operation point of view, we try to handle that uncertainty. So we are talking about the market. So there are different markets are available, okay, to handle the uncertainty. And what are these markets? So if I talk about very first is basically long-term bilateral contracts. So I will say bilateral contracts. So with the help of, let's say, a demand, a distribution company is trying to secure certain quantity or for its consumers, then it will go into bilateral contracts and procure certain quantity from the different generators available. But it is a long term, basically bilateral contracts are week to years ahead. So you are basically procuring a certain quantity so that you are provides basically some of the consumers. It can be more, it can be less. So whatever the quantity procured in bilateral contracts can be more than maybe in future you need, or it can be less as well. Once you are basically close to the point of delivery, uh, that is basically we have day ahead market. So we have day ahead markets, and as per the market philosophy, let's say if you have procured more in bilateral contracts, the company will try to sell it, or if you have procured less in bilateral contracts, then you have to procure more power in day ahead market. So, because but in the head, we will have better forecast as compared to the bilateral contracts, because those are weeks to year ahead. Bilateral contracts, day ahead markets are basically one day ahead, so you will have a better picture. Then certain intraday markets are also there. So those are basically like 6 to 4 hours ahead market, and in that uh, scenario you will have more better picture, and then you will try to adjust your schedule so that you make maximum out of the quantity procured. So either you sell it or you procure more. Then some real time markets are also there, okay, and those markets are generally called balancing markets as well. Okay, so we have balancing markets where we at the last minute we have exact or basically very much good forecast, and we will try to balance out our needs basically. So all the like whether generation company or like distribution companies, they will basically balance out everything in the last real time market, and it is the last resort. But still, it's uncertain. Okay, forecast is accuracy is more, but it is not 100%, right? So then we have the everything goes into the system operator, and then in balancing market, basically system operator balance out everything, and still if something is left out, the reserves will take care of that unbalance. Otherwise, our the first assumption is supply demand balance has to be maintained at every time. Okay, so how to model this uncertainty? So to model the uncertainties, we one of the ways is stochastic programming. In a stochastic programming, basically, we model this. So if you see here, there are different stages where we have to make decision. Like so, at bilateral contact, we have to make certain decision. Okay, so we have to make certain decisions that how much we should basically acquire in the bilateral contacts. Then we have in the day-ahead market, we again have to make certain decisions that how much quantity should be procured or in the day-ahead market. Then in intraday market as well, we have to make decision. And real time is basically last resort, so we don't make any decision. It's basically up to the system operator, and he decides everything. But again, somebody is going to make certain decisions there as well. Okay, so there are basically multiple stages of decision making. So we model those multiple stages in the stochastic programming. So what we do is here, let's say a very simple example is, let's say one stage is here, another stage is here. So this is first stage, then this is my second stage, and I'm trying to solve some x variable here and y variable here. But here I have to make certain decision. Now what happens that between x and y, again it's a like you will have certain forecast that this is the probability of some input basically parameters, and based upon those probabilities we basically create some scenarios that these scenarios can realize. So basically we will have multiple scenarios available with us in the stage 2, and based upon that stage, let's say so these are basically multiple scenarios. Okay, and I'm calling them w or omega. Okay, so these are the different scenarios. So based upon these scenarios, in the very first stage we basically make a decision about variable x. So these are called here and now decisions, and in this we basically make the decision about the x variable. Okay, so whatever is the x, whatever is the optimal value of x at the first stage, we will try to solve it. Then in the later second stage, let's say if we are talking about those are basically called wait and see decisions, and here we will make the decision about the variable y. So this y will basically we will optimize the variable y, and the y decision will depend upon x and multiple scenarios present in the system. So this is our so you can call it like this particular example is two stage stochastic programming. Then just understand this thing with a particular example. Let's talk out consider an example. So let's assume a demand. Okay, and demand has to make certain decisions, and let's say for a week, so demand has to make some decisions that how much should be procured in different markets, and this is the market options are available, like bilateral contracts, and let's say the uh, pool market or our day ahead market. Okay, so these are the different decisions available, and for a week, let's say, which is 7 days. Okay, so let's assume it already had basically certain contract with the supply end, and the contract is basically, let's say, a maximum of 90 megawatts, and at the price of, let's say, $45 per megawatt hour. Okay, so that is the already given us. Now it has to make a decision, the demand, that how much it should basically procure from out of this 90 megawatt, which is bilateral contract. So some contract is there with certain generating company that it can supply 90 megawatt at the price of $45 per megawatt hour, and then it has certain basically pool market scenario. So this day-ahead market is not realized, so we will have some forecast, and we have one forecast is that that its demand will be 110 megawatt, the prices will be $50 per megawatt hour, and the probability will be, let's say, 0.2 is the probability. So these are prices, these are probabilities, and this is our demand forecast. Okay, so these are basically different. Like one scenario is that there is a 20% probability that demand will be 110 megawatt and the prices will be $50 per megawatt. Okay, then another second scenario is that there will be 100 megawatt demand. The prices will be $46 per megawatt hour, and the probability of this scenario is 60%. Okay, then I can have another scenario that demand will be only 80 megawatt, the prices will be 44, and the probability will be 20% again. So let's say there are three scenarios. Now how can we model, and how the basically how much quantity should be procured in the herd market? So for different scenarios, we have to basically look upon, and decision maker will decide based upon the probability of the scenario. But we should give a expectation of the expected solution, that what will be the expected solution if we are looking at this particular data. So there are different kind of formulation for the this particular programming. Here basically, let's talk about formulation number one. So very first formulation, if we talk about, so what we have done here, like in this particular formulation, we will assume that there are two stages, and there are three different scenarios available. Okay, so this is one scenario, this is a third scenario. So this is my first stage, and this is my second stage. So first stage is basically about the uh, contract, that how much quantity should I procure from the bilateral contracts, and second decision is how much should be procured from the pool market, or we call it day ahead market as well. So one variable will be whatever is the contracted quantity. And then in pool market, let's say what will be the P1, what will be the P2, and what will be the P3. So this will be basically for scenario 1, what will be the power procured in the day-ahead market, P2 and P3. So for different scenarios we have. This scenario has the probability of 2%, this scenario has the probability of 60%, and this scenario also has the probability of 2%. Okay, so we have these scenarios, and let me name the scenario W1, W2, and W3. So these are the scenarios. Now, how to model these basically? So the demand will try to minimize the cost. So let's say we are minimizing the cost, and it is for basically entire week. So that is 7 into, and let's say 24 time periods has been considered. So 7 into 24 is how much? How much is 7 into 24? I think 168. Okay, so we will use 168 here, multiplied with the 45 is the price for the bilateral contract. So if is wants to procure some quantity, that will be the at the rate of $45 per megawatt. So this is one scenario. Plus second scenario is basically how much it can procure. So that is like 50 is the price, and P1 is the quantity which it can procure from the uh, second scenario. So let me name it here. Like in the very first scenario, it is basically this. So demand is 110 megawatt. Okay, and price is 50, and probability I have mentioned here, it is 146 at the rate 46, and this is 80 at the rate 44. Okay, now one can question that why the demand is making a decision that how much it should procure from the bilateral contracts, because it can acquire the entire quantity from the bilateral contracts, and then whatever is the remaining, it can basically go into the your pool market. So that question can arise. But if you look at these scenarios, the prices, if you look at, so the very first scenario price is roughly around 50, and our bilateral contract price is 45. So for the first scenario, let's say if it is deterministic decision that demand is going to be 110, I will simply, and the price will be 50, let's say, I will simply select that I will acquire 90 megawatt from the bilateral contracts, and remaining will be acquired at the rate of $50 basically. If I look at the second scenario, the price is still more, 46. So in that case, again, I will say that, okay, 90 megawatt will be acquired from the at the rate $45 per megawatt. And for second scenario, remaining 10 megawatts can be acquired at 46. But if you look at the third scenario, the prices are cheaper in pool market. Okay, so it may happen that bilateral prices are more. Generally pool market prices should be high. It's again, but it's not compulsory. So if prices are lower, I will not use entire bilateral contract because the prices are 45 there. So what I will do is I should basically reduce the consumption from the bilateral contract, and I should go with the pool market because I have to pay less. So that is the objective of a demand, that it wants to pay as much little as possible. Okay, so I will acquire the entire 80 megawatt at the rate of 44, and then remaining I will ask for the bilateral contract. Okay, so, and if some minimum limit is there, I will go with that particular minimum limit. So this is what I have I'm basically mentioning here, that we can have this 50, then at the 46 I have to make a decision plus for P2, and then I have to make a decision for 44 for the third scenario. Okay, so this is the basically this is what I want to minimize. But the probability of this first scenario happening, like the prices are being $50 is 20 only. Okay, so 20% I will multiply. This is basically 60. So the value will be 60, and then we have again 20%. So this is going to be my objective. In generalized form, I can write it down like this is 168 and 45 and whatever is the PC plus I can say like I'm doing a scenario over a summation over scenario, the probability of scenario, whatever is the price of that scenario, and then whatever is the quantity being cleared of that particular scenario. This value is basically a expected value of cost. So this is the expected cost. It has not been realized that this 110 megawatt demand is not realized. It is just a scenario. So if I go with these probabilities, I can calculate the expected value of the cost. So this is going to be the expected cost basically. Now, what should be the conditions? So in this particular optimization, we will write down certain conditions that the PC plus P1. So this is the scenario number one. So this demand, like whatever you have procured in bilateral contracts and pool market, should be greater than and equals to 110. That it should be at least 110 because this is the scenario that the demand is going to be 110. So the total procurement from the bilateral and the pool should be 110. Similarly, we can write down that PC plus P2 should be 100. Okay, and then we can say that PC plus P3 should be 80. So these were the demand scenarios. So we have written it. Now, what can be the PC value? So like we have to provide limits to these particular variables. So we have defined four variables here. So I will put that my PC and let's generalize pi are the variables. So I have four variables. I have to put a limits on this. So the PC I can go that maximum it can I can procure from the bilateral contract is 90 megawatt. Okay, and the minimum it can be, let's assume for this time that zero. If certain conditions are there in the agreement that okay minimum you have to procure 10, then we can put that here. But for this particular example, let's say the zero is the bilateral contract that it can also go up to zero. Then all the like P1, P2 and P3 we are procuring from the day-ahead market or the pool market. So it is the procurement by the demand, so it should be positive and it can go up to any value. Okay, that okay they can go up to any value, but these three conditions will limit the value of P1, P2 and P3. Now, if I want to solve it, what will be the solution for this particular problem? So if we solve, the PC value will be 80 megawatt. Then P1 will be 30, P2 will be 20, and P3 will be 0. So this is the outcome of this particular solution. And if I just calculate whatever is the objective function, which is our cost function. So the optimized cost will be basically, if I put these values in our objective function, I will get 747,936 dollars. Okay, so this will be the values. Just to give you that, usually the dollar symbol comes before the numbers. It's $747, but we are just putting the numbers and I'm mentioning the unit at the end. Okay, so this is what the solution will be for this particular formulation. Another way of formulation is basically there can be a different formulation. Uh, Formulation 2 is basically what we can do is we can have again three scenarios. So we still have three scenarios, the same probability, same data. But we can model it that this PC will also be calculated here, and P1 will also be calculated here. Okay, and everything we are doing in very in advance basically. So it's not about like in the day-ahead market we are making the decision of PC. We are just assuming like for the solution point of view that we can consider these as a this kind of modeling that we will try to solve what will be the contracted price for scenario 1, what will be the bilateral contract price for scenario 2, and then what will be the bilateral contract price for scenario 3. So for this particular problem, I will again minimize, and objectives will be PCI and PI. So instead of one PC, I'm assuming that for each scenario, there can be a different outcome for the contracted price as well. So we are considering that. So the cost will be equals to we have 7 into 24 for 1 week. So let's say 160 is the multiplier. Then what we can do is multiply this, and the first scenario probability is 20%. Okay, and then the for PC it is 45 is the price, so the PC1, and then 50 is the price for P1. Okay, plus there is a 60 probability, and then 45 PC1 plus 46 P2 plus 20% probability, and 45 PC3 plus 44 P3. Okay, so this is will be our objective. So far, if you have any doubts, please ask. Okay, you can always put the doubts in your chat box, or you can raise your hand. I'm continuously, having an eye on the chat box. If you have doubts, we can discuss at the same time. Then what will be the subject to condition? So the subject to condition will be that whatever is my PC1 plus P1 should be more than 110 megawatts. Whatever is PC2 plus P2 should have more than, the demand was 100, and whatever is PC3 plus P3 should have more than 80. Okay, so far everything is good. That this is the condition. Now if I put the variables limit, so let's say P1C, P2C, and P3C, these are the bilateral contract quantities. So they should be less than 90, and the minimum value can be 0. It cannot be negative, right? Similarly, in the pool market, we will have P1, P2, and P3. So these values can be basically anything but more than 0. So it should be positive. So these are basically the limits we have defined. But as I explained you that the decision making is two stages. There are two stages. One is we will make decision of the bilateral contract. Another stage we will make the decision for the pool market. So I have to put another condition that whatever is the PC1, it should be equals to PC2, and it should be equals to PC3. So this is basically this constraint makes them or couple the entire formulation. So if I, let's assume, do not have this particular condition. So if this condition is not present, you can see that there is no coupling between different scenarios. So there is no coupling between scenario 1 and scenario 2. So I can basically write it down like, there are multiple problems. So if this is not present, so if coupling is not there, I can simply write down that it's a minimization of post function of ith, or I would say W scenario. We assumed WS scenario, and that will be equals to 168 is the multiplier, and then pi w is the probability, let's assume, Okay, then we can multiply it with whatever is the lambda contract, so whatever is the bilateral contract price, and then our PC contract price for scenario 1 plus whatever is the scenario price for the day market, and so which was like 50, 46, and 44, and whatever is the price subject to, I can say that PCW plus PW should be more than whatever is the my power demand for that particular scenario. So we have 110, 180 demands, and then we can write down that this PCW should be less than 90 and 0, and PW should be sorry, greater than equals to 0. That's it. So if this coupling is not there, the entire above problem can be divided into three different problems and can be solved separately. But this coupling constants basically couple them, and we have to solve it together, that all of the contracts basically are the first stage decision, and they will affect the decision at the second stage. So these basically, like, and the very first stage, we have to make the decision about the bilateral contract. So if once it has been done, uh, they should be equal, and the solution will remain same here again. So whatever is the, like, solution, if I talk about of the above problem, is again same. We had PC1 equals to PC2 equals to PC3 equals to 80 megawatts, and we had P1 equals to whatever is the remaining, I think 30, P2 equals to 20, and P3 equals to 0. Okay, and same, the cost function will remain also same, which was, I think, the optimized cost was roughly around 747,936 dollars. Okay, so this is the solution. Now you can see that for this particular scenario, we had an option of a bilateral contract with a 90 megawatt quantity at the price of 45, but we are not utilizing the entire contract. We are only scheduling 80 megawatt based upon these scenarios, and this is in this way only the cost will be minimum. Otherwise, sorry, cost will be higher than that whatever we have calculated here. Okay, so I can give like write down a generalized multi-stage uh, formulation. So what we can do is, let's assume the very first step is we have to make decisions. Let's say x1 is the first stage variables. Okay, so decisions on x1 will are made. Then some stochastic process will be, so like different scenarios will be realized. So we will utilize those scenarios, and I'm naming that as stochastic process. Let's say what should be the name for the stochastic process? I think we have used, so let's assume gamma 1 is realized. Okay, so I'm naming it gamma 1, and some scenario basically in the first stage scenarios are there. So this omega 1 is first stage. Okay, then once the stochastic process is realized, we will make the decision of the second stage. Decision of the x2 will be made, and that will depend upon the x1 and whatever is the scenarios available. So we will made those decisions. Then same again, some stochastic process gamma 2 is realized, and let's name it gamma 2 scenario 2. Okay, and because of that we will make the decisions on x3 variable, and those x3 variables will depends upon x1, omega 1, x2, and omega 2. Okay, so different stages are there, and decisions on the different variables will be made in the subsequent basically stages. Okay, and we can basically repeat it to whatever number of steps we are looking at. Okay, so we can repeat this entire process. So if I make this particular diagram, like there is a one stage, then we have second stage, then we have a third stage, and in there are multiple scenarios basically. Okay, so I will put multiple dots here. Then there are multiple scenarios from this particular part, and so on. Basically, there will be multiple scenarios from this particular part to this particular part. So I will make different dots here that there are multiple. We have multiple scenarios over the last stage as well. Okay, so we can say this is my first stage, this is my second stage, and this is the third stage. And the variables here are basically x1, x2, and x3. And we have certain scenario omega 1 here and then omega 2 here, and based upon those we are making the different basic decisions. Okay, so so far I think it's fine and understood by everyone. Let's see an example of the three stage basically, that how we can model the three stage stochastic programming. So let's say generator is there. Okay, and he has to basically produce certain quantities, and you have to make the decision how much it should produce. Okay, so let's say there are 6 days. Okay, so this is d1, 2, 3, 4, 5, and 6 number of days are there. Okay, uh, the information is that bilateral contracts are basically like it can go for a bilateral contracts of 50 megawatts at the rate of $25 per megawatt hour. Okay, and for all 6 days, then it can go like 40 megawatt at the rate of $26 per megawatt hour for last 3 days. Okay, then pool market scenarios are also there. Okay, so there are certain scenarios in the pool market, and those scenarios are basically um, the prices for first days are basically two 27 dollars per megawatt hour, and the probability is 0.4. And another scenario is the prices can be $23 per megawatt hour, and the probability is 0.6. So this is one scenario. Then another scenario is there that prices are at $27 per megawatt hour in the first 3 days, or first time block, I would say. There will be, for the next 3 days, the prices can be 28 with the probability of 0.4, and then it can be 26 with the probability of 0.6. So if the condition is that if prices for the first 3 hours is 27, then for the next it can be like $1 higher or $1 less, and the probabilities are again zero point 0.4 and 0.6. And again it says that if prices are at this, then the prices can be like 24 with the probability of 40, and then $1 less, which is 22, and probability of 60%. Okay, so these are basically, so probabilities basically we can have. So it's basically like there are two scenarios that if uh, we can say there are the chance of getting a high price and low price, and then if this high has been realized, it can further go high and low, and it can also go certain high value and low value. So these are, let's say, certain input data is available, and based upon that we have realized these are the scenarios. So first of all, we will make a scenario tree, that how the scenario tree will look like. So if I talk about the scenario tree, we have is one. Then the chance of the prices are high and low is 2. And if prices are high, then it can further go high and low, and this can also go high and low. So these are the three different stages available with us. Okay. So the probability here is like 40%, 60%. This is also like 40% and 60%, 40% and 60%. Okay. Then so can you tell me, like, there are different stages. This is first 3 days, and this is basically last 3 days process. Here what we will do is we will decide upon the contract A, that how much quantity should be uh, acquired from the contract A, and contract A is basically valid for all 6 days. This is what we have identified, that contract A is valid for all 6 days. Then in the second stage, once the 3 days are over, we have to make a decision on the contract B, which is so okay, let me mark the validity as well. So our contract A is valid from for all the 3 days. Then we have contract B, which is valid for last 3 days only. But and we are assuming that the demand is constant in the this period. So here for the first 3 days, we have to make a decision about the pool market as well. So that will be made on the second stage, that okay, contract has been identified, contract A, and then based upon these prices, I have to basically producer has to produce certain quantity. So what will be that particular quantity? So we have to make the pool decision for the uh, previous days, and then we have to make the pool decision for the remaining 3 days. So these will be the decisions basically which we have to make here. Okay. Now, how can we do it? So let's assume the demand is constant. So I'm assuming that demand is constant and equals to 120 megawatt, because I don't want to make it complicated from the both the sides. Let's keep it from the generator side uncertainty, and demand is, let's assume, fixed for the time being. So how can we model it? So we had two different formulations. So let's say it's a generator, so I want to maximize the revenue. So whatever is the objective function, let's say maximization of this equals to, uh, I have to make a decision on the, like, pool market. So the very first data which we have is how much is the contract price for the first bilateral contract. So it is 25, 50, and 26. Okay, so this is basically we have. Okay, before going to that, can somebody tell me how many scenarios are there actually for this particular stage? Anyone, please put your answers. Like if you look at this particular scenario tree, actually how many scenarios are present? 16. Any more answers? 6, 16, 6. Okay. So let's see basically that how many scenarios are there. So let's look at the variables. Okay. So this contract A is basically for the entire 6 days. So I can say that this is PCA. This is the contracted price PCA. Now after that, I have to make a decision on contract B. So contract B will be basically having like whether a high price is realized, a low price is realized. Based upon that, I will make the two decisions on this contract B. And in pool as well, I will make the decision that how much the quantity should be there for the first days, and then what should be the quantities for the 3 days. So at the end, whatever is in the last stage, that decides the number of scenarios. So this is basically scenario 1, this is scenario 2, this is scenario 3, and this is scenario 4. So we have basically 4 scenarios here, only 4. Okay. And the probability of this scenario is basically that chance of getting a high price in first 3 days is 40%, and then further getting a higher price for the last 4 days is 40%. So the total probability is zero point 0.4 multiplied with zero point 0.4, which is 0.16. So this will be the probability of scenario 1. If I look at the second scenario, the chance of high price in the first 3 days is 40, and then further lower price is 60. So the probability will be zero point 0.4 into zero point 0.6. How much it is? 0.24. Similarly, this will be 0.24, and the next will be zero point 0.6, and zero point 0.6 is 0.36. And one important point is, like, whatever omega equals to 1 to, let's say, number of scenarios, if I talk about, the probabilities should be equals to 1. Okay, so this is the condition we basically always satisfies, that the probability can be 100% only, not more than 100%. Okay, so the probability of scenario 1 is 16%, scenario 2 is basically price of like uh, first high and then low is 24%, similarly third, fourth in 24%, and for the last it is 36%. So based upon that, if we try to basically write down the objective function, what we can do is we have to make a first decision about the contract A. So I can say that it is for 6 days. So 6 into 24, how much it is? 144. I am very I'm not good in maths, I think, so I did it with calculator. Uh, so 6 into 24 is basically 144 hours. And if I multiply it, the price for the first bilateral contract is basically 25, and I have to make decision that how much I should get out of it. So that is the, let's say, contract A. So whatever is the power in contract A, that will be here. Then there are two scenarios that it can basically the probability of the prices being higher is how much? 40%, and that is for next 72 hours. Okay, so what will be those? If I multiply it, I have to first of all make a decision about the contract 2, which has the price of 26, and I will make decision about the PB. But at the same time, there is another scenario that basically 60% chance that the another scenario will realize. That is again 22 is the time multiplied, and the prices for the contract is fixed, but I will go with another PB. So let's name it PB1, and let's name it like, let's say, PB12 and PB34. Okay, so this is basically I have mentioned here that these are the variables for me. Now further, if you see, if point 4 scenario is realized, there is a chance that we acquire what was the price here? $27 per megawatt hour, and this was basically $23 per megawatt hour. These were the prices here. And if I look at this particular one, this was 28, this was 27 to 26, this is 23 to 24, and this is the price is 22. So I make a decision. Okay, let's delete these first. So if first scenario is basically being realized, what we will do is, okay, the probabilities are these, and then we have to for first 3 days we have to basically procure certain quantity. So the prices of the market is basically 27 for the higher price is 27 for the first 3 days, and let's say this is P1, and let's assume that first 3 days are defined by T1. Okay, so this will be the one variable, that how much quantity will be supplied in the T1 duration and then T2 duration. So I will put it 27 into T1, and the below was 23 into basically we can name it the 27 is for scenario 1 and 2, right? Because if you look at this particular one, this 27 price for the first 3 days is for scenario 1 and 2, and this 23 is basically for scenario 3 and 4. And whatever is the contract as well, that is basically like whatever we are going to do with the contract B here is for scenario 1 only. So that's why I have mentioned certain subscript. So I can say this is 1 2, and this is like for second time, and this is equivalent to 3/4 number scenario. Once these scenarios has been like the demand pool market, so this is contract A, and this is our pool quantities. Okay, now I have to go for the contract B. So I will put the contract B. Contract B was the price of 26, and this is price 1, and this is valid for both the scenarios because it will remain same. And then we have basically price of same 26, and it should also valid for 3 4. Okay, so this is the contract price, that okay for the second time period what will be the price for the our contract B prices. After contract B prices are over, we will look at the pool price or pool scenario for the next time duration. So we again have further is like 0.4 is the probability, and the prices can be further more, which is 28, and then we can put like T2, and the scenario was 1 plus 0.6 is the probability, and 26 into second time period, and the quant scenario was T2. So this is it. Plus similarly, I can put this is 0.4 into 23 to 24 into second time scenario 3, and then 0.6 into 22 into PT2 and 4 scenario. So this will be my objective function. You can see there are a lot of variables here. Okay, but finally, we will end up with this objective function. Now let's talk about the constraints. So what is the subject to constraints? So constraints are for the first 3 days, whatever is the bilateral contract plus PT12 should be less than equals to 120. 120 is our demand, fixed demand. Then whatever is the PA plus PT1 3 4 should be less than equals to 120. So this is basically for first 3 days. If I talk about next 3 days, whatever is the PA which is valid for all the 6 days, then plus whatever is our PB12 plus PT21 should be less than 120. Then whatever is the PA plus PB12 plus PT2 second scenario should be less than 120. Then we have third scenario, so which is PA plus PB. Now it is the bilateral contract second on the second scenario, basically lower price in the first 3 days. So that will be 3 4 plus PT2 3 should be less than equals to 120, and then we have PA plus PB 3 4 plus PT2 4 less than equals to 120 megawatt. So these are the conditions. Apart from that, we will have certain limits. So the limits are like PA can have a maximum of 50 megawatts, which was given earlier. Then both of PB either 1 2 or PB 3 4 can have maximum of 40 megawatt. Okay, and then all of our PT2, whether it is 1 2 3 and 4, should be positive in the pool market. Okay, and all of our PT1, which is like 1 2 and 3 4, and they should also be positive. Okay, so this is what we can write it down. And if I look at the solution, what will be the solution for this particular problem? Okay, who can tell me, like, if you look this particular problem, this objective function, let me bit zoom out. This particular like objective function, and these are the constants. Can anybody tell me what kind of problem it is? Whether it is linear, non-linear, or quadratic? How we can solve it? Anyone? If you look at this particular problem, whether it is linear problem or non-linear one. Non-linear, linear. So let's give the name. So let's assume this is equation number 1, equation number 2, 3, 4, 5, 6, 7, 8, 9, and 10. Gaurav, which equation is nonlinear or objective function? So there is a one objective function, and then we have 10 number of equations. Which part is nonlinear according to you? Like where the nonlinearity is? You are saying in objective function. Shilpa is saying it is linear. So actually, this entire problem is linear. And if you have doubt that it can be non-linear, basically, and the doubt is basically, let's see at the look at the objective function. Wait, adjust it. Yes, here. So in the objective function, we have different basically terms. This first one is a constant multiplied with a variable. So this is linear. If you look at the second term, this is a constant. Okay, this particular part is a constant. Then none of the variables are basically have a higher power. It's only single variable, right? They don't have any like power is not uh, either less than one or more than one. They have all the variables are basically have a linear power, which is power one. So if you look at here, 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 and here, everything is linear. So this problem is linear, and we can easily solve it, and you will get a perfectly global optimal solution. Okay, so the solution which we have, so I have written it down with me that your PA will be 50, okay, and PB12 will be 0, and PB34 will be 40. So it says that the generator should go into bilateral contact for the entire duration, and the quantity should be 50 megawatt, but it should not go to the bilateral contact because for the if prices first scenario the first 3 days if prices are going into higher side, it should not basically go into bilateral contact, because that's why this like PB12 is coming equals to 0. And if the prices are low in the first 3 days, then it should again end up going into the bilateral contact B of the 40 megawatt. And then if I talk about like what will be the PT1, it will be equals to PT2 equals to 70 megawatts. And then if I talk about whatever is the PT2, okay, and for I think all the basically part we will have so 50 plus 40. Then if it is goes by like market 70, then 50 14 how much is the total demand? 120, right? So 50 40, so how much? 90 30 will go basically. So they will go into PT2 will be equals to 30, right? So total demand is 120. First is 50 megawatt. For the second time period, 50 megawatt is already secured. So how much is left? 70 megawatt. And if bilateral contact of 40 happens, so let's say bilateral contact of 1, so P1 will be equals to PT2 2, and that will be equals to how much? 70, I think. Yes. So this is not 30, it will be 70. And then we have PT2 third scenario, that will be equals to PT2 fourth scenario. And for 3 4 scenario, 50 and 40 megawatts has been basically acquired from the bilateral contact A and B respectively. So remaining is 30 megawatts. So this will be the solution. Okay. Uh, do you have any doubts so far? Now, can you make second formulation for me? can you guys make a second formulation for me? And I will just give you, 5 minutes of time to do so. And how will decide about bilateral or pool quantities? So this basically we have modeled it in multi stages. So in the different stage, and based upon those stages we have basically formulated our problem, and after that formulation we will end up with a particular solution. So if you look at like the question is like for bilateral contract A, it is a uniform solution that 50 megawatt should we should end up with 50 megawatt. Now the question is how to decide out of these two, that how much we should go into bilateral contract B. Okay, contract B. One answer is saying you should end up with 0. Another scenario is saying that it should be 40. So here is the catch, that it's very difficult to decide because everything is uncertain. If you see, the probability of the first scenario is 40% and probability of second scenario is 60%. So if I go with the literal probability and say that okay, 60% chance is there that prices will be low, and based upon that I should go with the bilateral contract of 40 megawatt. But generally from the like research point of view or decision making, we always calculate expected value, and that expected value for PB will be equals to 40% of 0 plus 60% of 40, and that value will be, I think, 24 megawatt. Okay, so this is the expectation. Now the decision making will depends upon how much risk a decision maker is willing to take, and based upon those risk values, so we will talk about those different risk measures as well, that how to make a decision. But let's say if I'm not talking about the like risk and all, I just look at the expected value, that over all the probable scenarios what should be the basically probability. Based upon that I can decide that okay, I should end up with that 24 megawatt bilateral contract. Here it's like to visualize this scenarios for the contract B. But if we create, let's say, thousands of scenarios, I'm talking about thousands of scenarios, in that case uh, they will basically able to model the randomness more accurately, and the solution will be most of the time, again it's not 100% sure, but most of the time the solution will be equals to the whatever we are expecting. And this is how we can basically make a decision for the uncertainty, that okay, whatever is the expected value, so this is the expected value, or this is the mean value. So you can also call it mean value, right? Because we are basically averaging it with respect to the probability. So this is also, you can say, mean value. So you can go with the mean value. And if you are like risk loving decision maker, you can also go with the 40 megawatt, that okay, it's okay, I will go with the higher side, or I can go with the lower side. So that depends. Similarly here, like PT1 PT2 is 70%, 70 coming close to 70, so that decision is already made. But if I look at the second time period, I again have two solutions. So expectation of PT2 will be like for 1 and 2 scenario, it is 0.16 into 70 plus 0.24 into 70 plus 0.24 into 30 plus 0. I think 0.636 into 30. So these were the four scenarios, and we can calculate the expectation of the second time, so like how much we should go in the pool market. So this is how we can calculate the expectation. The final decision has to be made by a decision maker, how much he wants to do. Or now, if I ask you formulation two, can you tell me for this particular problem how we can do? Just think about it. I will just take a quick break of like just 2 or 3 minutes, and I will resume. So just don't go anywhere. We will resume in 2 or 3 minutes. So we'll resume again. So if I look at the second basically formulation, so let me take my pen. Second formulation is again like so maximization of, let's say, some variable C, and what I have to do is I have to maximize the four scenarios. So here what we will do is we will like just like earlier in the second formulation, this particular one, the all the variables basically we are solving at the last stage. So similarly here as well, we will try to solve everything at the last stage. And so let me draw first the like multi-stage diagram. So what we can do is we will try to solve it. So this is the very first stage, then we have high price, low price, okay, and then this is the second stage. Then we further have a high price and low price scenario, and then we have a high price and low price scenario, and these are my third stages. Okay, so I have to make certain decisions. So this is scenario 1, scenario 2, scenario 3, scenario 4. We have calculated the probabilities of this scenario, this entire scenario being realized. That first prices are how much? I think at 27, or how much the price earlier? Let me see. So the very first is basically how much will be the prices. Higher price is, I think, at what will be the prices for 27. The probability was 0.4. The prices were at 23. The probability was 60%. If high price goes, the further prices will change to 28, and the probability was zero point 0.4. So I will mention those here, like the probabilities we already calculated. So these are like 0.24, 0.24, and 0.36. These are the different probabilities of these four scenarios. Then we will have like realizing this particular scenario, we will have a variable that what will be the PA variable, bilateral contact for scenario, entire scenario 1, where high prices are there. So okay, I can also, like, W1 is basically high scenario, W2 is basically high low, W3 is basically low high, and W4 is also basically low and low. And sometimes, like, while putting everything in the programs and all, we make that, okay, one scenario is basically like, price 1 are basically high and low, and then price 2 is basically again high and low, and based using these two information, we club them up, and we will end up with the four scenarios. So, like, we merge them, and we decide that, okay, there will be total number of four scenarios. So PA1 will be the variable. Then certain from the bilateral contact 2 for the first scenarios, then certain thing from the T1 from the first scenarios, and certain thing from the time period 2 from the first scenario. Similarly, we will have A2, B2, PT1 2, and PT2 2, and similarly we will have 3 and 4 as well. Okay, so these will be the variables. Based upon these variables, Kush, am I audible? I have unmuted myself, right? Yes, thank you. So, based upon that, I will write down that we will maximize the profit. So, let's say profit of the stochastic process is basically the first scenario probability is 0.16. Okay, it's visible. No, now it is visible. So, first scenario probability is 0.6, and then I can basically solve it for how many times. So let's say into PA is basically available for how many times? Entire 6 days. So 6 into 24 will be equals to 144. So that is 144 time periods into, we have the price for the bilateral contact is 25, and then we will put a PA1. So this is the decision making on PA1, that okay, this is what we are getting if we are providing some power with the help of contract A. Then plus we have contract B, that is only for the last 3 days. So the time period is 72 into the prices were 26, okay, into, and this is PB1 plus. Now let's talk about the time period one. So the prices were at 27 for the pool market. So this will be also like 72 hours, because the first uh, 72 hours, and then we have further 72 hours. So 72 hours, and prices were 27, and then PT1 first scenario, plus then we have prices of 28, and then it was 26 with 0.6 probability. So what I will do is I will put 72, the letter 72 into 28 into PT2 1. This will be the profit over first scenario. Then I can put it is the same value 24 into, for this particular part, uh, this part will remain same, and I will put PA2, plus this part will remain same, and I will put PB second scenario. Okay, here plus this part will remain same, and I will put T1 second scenario plus 72, and the price for the T2 time period for this second scenario is, instead of 28 it is 26, so I will put PT2 2. So this is the third scenario. Then I will have the fourth scenario, which is 24, and prices are again same for the very first one. Okay, so I will put PA3 plus the contract price for the contract B is also same, so PB3. Okay, and then this prices has been changed. So instead of as 27, the lower price was 23 into this is third time period and time block 1, plus 72 into higher price was 24 into PT2 and 4 scenario. So this is basically the last, and is similarly the last scenario will have the same values, and PA4 plus constant is the same, and PB4 plus this is the low price, so PT1 4 plus 72 into 22 into PT2 4. I made a mistake, I think. This is not 4, this should be 3. Yes. So this is third scenario. Okay. So this will be the objective function now. So like for all crystal clear 4 scenarios, we have defined that all the variables are distinct. So pool A also have 4 different values, pool B also have 4 different values, and similarly time block 1 and time block 2 of the 3 hours have the same values. Now if I look at the subjective condition, this PA1 plus PT1 1, so the first 72 hours the demand should be 120, that is fixed. Similarly we can say that PA1 plus uh, PT1, if we talk about, so like first time block PA1 and PA2 second scenario, and whatever is the PT1 2 should be 120, and similarly I can put it here like PA of the third scenario plus time period 1 of the third scenario should be 120, and similarly PA 4 comma sorry plus PT1 4 should be less than equals to 120. So this is for first for 3 hours. Then later on 3 hours we'll have PA1 plus PB1 plus PT21, and that should be 120, and we will repeat for second, third and fourth scenario. The same constant with instead of 1 there will be 2 mentioned here. Now the thing is the limits on these variables, if I talk about whatever is the PA like 1, whether it is, and PA and PA for all the scenarios will have a maximum limit of 50 and minimum limit of 0. Similarly, PB1 to PB4 will have maximum limit of 40. So these were the defined, and all of these basically other variables like P either T1 or T2 and either 1, 2, 3 and 4, they should be positive. Okay, so this is the condition. Now we have defined four different variables for by contract A and four different values for contract B. But we know that the first stage decision has to be made first. So that is here and now decision making. Then second stage decision will be made as a wait and see decision. Between 2 to 3, second stage decision will become here and now, and third stage decision will become wait and see. So they are basically interdependent and they cannot have different values. So we will put some non-anticipating constants, and those are basically or we can say coupling constants. So I would say that PA1 should be equals to PA2 should be equals to PA3 and should be equals to PA4. That the contract A is uniform over all the scenarios. Okay. Another constraint is that PB1 should be equals to PB2. That contract B decision will be made upon whatever is the PA decision, and if high prices are there, I will make certain decision. But with high price, there are two multiple scenarios, scenario 1 and 2, both will have the same decision making. This is here and now. And if like in the to second stage, if low prices are there, so that is scenario that will end up with scenario 3 and 4. So here the 3 and 4 should basically be made equal. Again, the thing is about the first time period, the same thing we will do, that the for first time period they should be equal, the pool prices, because they will depend upon the whatever you are decision making in the whether it is high price or low price. The other so we only realized the prices of 27, and earlier it was, what was the prices, 27 and 23 for the first 3 days. The next was like 28, 26, 24 and 22 were for the time period 2. So for the two prices, the both of these should also be equal. And similarly, we can say that at T1 3 should be equals to PT1 4. So these four constants are basically six constants will couple them, and the both the formulation will then become same, and the solution will be the same as well. Whatever the solution we have obtained in the previous case. Do you have any doubt so far? Now let's talk about some quality matrices. What are the different please discuss coupling constants. Okay, so if you look at this decision tree, and I just keep in mind the very first decision tree which we made here, that whatever decision contract A will be made, it is valid for all the 6 days. Okay, contract B decision will be valid for last 3 days or second time block, I would say. So this is valid for T2 time. So this is for T1 T2, this is for T1 plus T2 time. The first pool decision will be made at the second stage based upon the 27 and 23 price. So this is for T1, and second pool decision will be made with the help of that time period 2, which is of 3 days, and the last 3 days basically. So if you just keep it mind, and we will go back to the our scenario tree which we made. I think this one. So the variables here are basically you will make a single decision here, PA, but we made that okay for each scenario we are assuming okay, we are assuming PA1, PA2, and similarly, like PA3 will be there and PA4 will be there. So for each scenario, we are considered four different variables, but they will they should be equal. So that's why we will make them equal so that we get the same value, which is here and now decision in the stage one, and it will remain constant over the entire 6 days or both the time period T1 and T2. Now the second decision is about uh, let's talk about, so this PA has been considered. Let's talk about the PT1 time period one. So this PT1 decision is basically pool decision, pool market decision at the second stage. Okay, so this was the first stage. At the second stage, and it will be decided by the pool market price. So pool market price of 27 high and 23 low. So based upon that, we will decide how much will be the PT1 and how much will be the PT2. But if you look at this PT1 and time period 1 P2, so we have defined two variables, but both of these scenarios are basically are coming from the 27 price. So these T1 powers will be equal or should be equal. So that's why we made a equality constants here, that for scenario 1 and 2 are in the time block 1, the both P1 and P2 are same, and they are defined with the price of this 27. Similarly, we will have some PT1 3 and PT1 4, and they should be equal as well because they are decided by the price of 23. Okay, so that's why we made it as well that both of these pool prices or pool powers should be equal in the day market. Power should be equal. Now let's look at the contract B. Okay, so for contract B, yes, I think you got the point, right? So similarly, like contract B will be made here and now decision. Contract B will be made a decision at second stage, not at the third stage. So both of these P B 1 and 2 will be equal, and similarly the PB 3 and 4 will also be equal. But if you look at the PT2 1, PT2 3, they are basically made at the third stage, at the pool decisions. Here, if you see, the prices are different for all of these, like 28, 26, then it is 24, and then 22. So those values will be different. So that's why we have not may basically defined that constant that the powers at T2 are equal. Powers at T2 are completely different, and they are basically positive only. So this is what we have defined. Okay. Now, if I look at the quality matrices, there are two quality matrices. One is basically okay. Let me change the color. Expected value of perfect information. So very first is EVPI, and second is value of stochastic solution, VSS. These are the two matrices. There are others as well, but we will discuss about these. So what these metrics are basically. So EVPI is basically gives you the quantification of perfect information. Like if I want to acquire the perfect information or basically accurate information, how much I should pay. So let's say a decision maker is there, and there are, for this a previous example, a generator has to basically decide how much quantities for contract A, contract B, and for time block 1 pool, and for time block 2 pool market. So, and the decision is affected by the prices. Basically, those are the uncertain values there, because we consider the demand is known, perfectly known to us, that was 120 megawatt. So the only thing which was varying was price, that there are prices are different. So how can we know about the prices? So we can know about the prices by getting that, like, forecasting tools. So forecasting, we have to spend on the forecasting. So that is some money we are putting on the forecast techniques. And just hypothetically, assume that, okay, to get better accuracy, and not hypothetically, like it is understood that to get better accuracy, you have to put more money, so that your tools, forecasting tools, are robust. So obviously you have to spend more. So you are spending some money to get accurate forecast from some, let's say, some companies there who perform the forecasting and who has forecasting tools. Okay. So based upon that, you are paying some money to a company. So let's assume now, this time, like, if you are able to get perfect information, everything is known to you, uh, how much you should pay for that perfect information. So that is the first matrix gives you EVPI, that what is the expected value of the perfect information. So if your objective function is have less value, and let's say, so you solve with uncertain information, like all these scenarios. So we have solved it with uncertain information. Second is, we solve the same problem with the perfect information. And whatever, how much money we are making if we have perfect information. So that difference is basically the expected value of perfect information. So if that difference is like this much money, we are ready, we can pay to for acquiring the perfect information or accurate information. So this uh, metric is for decision maker, and it gives the, like, willingness to pay to obtain perfect information. So this is basically, you can say, it is willing to pay for obtaining perfect information. So that is one metric for a decision maker, that how much he can pay to get the perfect or more accurate information. So it's basically one measure. Sorry. Second is VSS, value of stochastic solution. Here basically it is measured to quantify the advantage of stochastic modeling over the deterministic one. So this is basically a measure to quantify the advantage. Stochastic programming over deterministic one. How we can calculate? We will see. So first of all, let's say the objective function is basically of minimization, and generally we minimize cost. Okay, that is the value, right? So if we are minimizing the cost, the expected value of perfect information for a minimization objective will be equals to whatever solution we are getting from the stochastic process that we have solved earlier, minus whatever we are getting with the perfect information. Okay, so if we have perfect information, the cost will be further less because we are more accurate now. So whatever is the difference will give you the EVPI. If my objective function is of maximization, generally let's say profit or revenue, then EVPI for a maximization objective function will have the value of ZP optimal minus whatever is the solution we obtained from the stochastic process. So if we are maximizing our profit, the stochastic profit will be lesser, and the perfect information like everything is known, that profit will be higher. So we'll get this, and this basically implies that EVPI is always a positive number or non-negative basically. So this implies that it should be positive only. Okay, and let's discuss. So we still have a few minutes left. So earlier we had an example, right? That one example we discussed earlier. Okay, we were minimizing cost, and the objective was, okay, let me go back, for a demand of certain, like, two stage one, because it is easier to understand, like we can easily understand this particular part. For I think this particular problem we can discuss. Yes, this one. So if you see, let's say for this particular problem, the 168 was time. There were three different probabilities for three different demands of 100, 10, 100, and 80. And there is an option that we can go in the bilateral contract for a here and now decision, and then remaining quantity can be procured in the day-ahead market with basically uh, wait and see as a wait and see decision. So if I look at the values here, like the optimal value was 747,936. Now let's see if perfect information is available, how the model will look like. So let's say everything is known. So in that case, how we are going to solve it? So we have three scenarios, and we are assuming that those three scenarios are going to be realized. Okay, so the objective function will become like, okay, in this particular modeling, we will get rid of this particular equation. We will remove this one, that all the contracts are basically have the different values, and we will look at that, like these three scenarios are there, and based upon three scenarios we will try to model the problem. So we have a 20% scenario into 168 was time, into, let's say, 45 was the price for the bilateral contract, and PC1 plus 50 P1, and plus 60 into 168 into 45 PC2, plus 46 was the price for P2, and then 20% into 168 into 45 was the price, and PC3, this is C. Okay, plus 44 was the price for the third scenario. So these were the scenarios, and if we solve that deterministically, uh, we will get rid of that particular equation of multiplying. So subject to this PC1 plus P1 is more than 110, uh, PC2 plus P2 is more than 100, and PC3 plus P3 is more than 80. Okay, and we had that this PC1 oblique 2 oblique 3 is less than equals to, I think it was 50. Okay, you can check it. I think it should be 50, and then P1, P2, and P3 are positive. Apart from that, earlier, like formulation we had is constant that PC1 should be equals to PC2 equals to PC3. These are the contract prices, so they should be equal. But to obtain the info, like perfect information solution, we assume that we don't need this particular part, and we assume that we are very much certain that 110 has the probability of 20%, 100 has the probability of 60%, and like the third scenario has the probability of 20%. In that case, if I try to solve it, what solution I will have? So here the solution will be like PC1 will be 90, and P1 will be 20, PC2 will be 90, and P2 will be 10, and if I solve it, PC3 will be 0 and P3 will be 80. As I explained you earlier, this thing is that if prices are 50 in the third scenario, as a rational player, I will see that okay, there are two prices. Either you can pay 45 for the contract and 50 in the pool market. I will definitely okay. So this limit was 90. This limit should was 90. So I will definitely acquire maximum from the bilateral contract because it is cheaper, and whatever is the remaining I will go in the pool market. So that's why you can see it is 90 megawatt. The entire thing has been acquired, and to fulfill the demand of 110, the 20 megawatt is basically procured from the spot market. So if we have the perfect information, I will definitely make that particular decision. If I have perfect information that the pool market price is 45, and sorry, 45 is the bilateral contract and 46 is the pool price, again the contract prices are lesser than the pool price, so I will definitely go with this answer that acquire maximum from the contract, and whatever is the left out I will go in the pool market. So the 10 is left out, so that's why the P2 will be 10. For the third scenario, you can see that the contract price is expensive than the pool price. So I will try to acquire everything from the pool because it will be the cheaper for me. So that's why you can see here it is 0 and here it is the entire 80 megawatt is basically acquired from the pool market, and we basically the procurement from the PC2 is 0. If I put all of these values in this particular objective, C, I will get as C P star, and that will be equals to 742,560. Okay, and we earlier obtained a C stochastic solution that was 747,936. So we can basically calculate our expected value of perfect information. Okay, so the expected value of perfect information, and the objective was basically our minimization. So I will put a minimization that will be equals to um, value of stochastic solution minus value of perfect information solution, and that will be like 747,936 minus 742,560, and that is equals to 5,376. So this is the expected value of perfect information. Okay, so it is always positive, and you can also sometimes call it this part as a cost of uncertainty. Cost of, because of uncertainty, we are basically we will end up losing this much value. So you can also either it can be like value of information, or the like how much you are willing to pay for to get the accurate information, or you can also say like because of the cost, this is the opportunity cost which has been lost. Okay, so far I think any doubts if you have, we can discuss. And the value of stochastic solution we will discuss at 2, and then we will quickly move like how we can use this entire stochastic programming and the concept of these, and we will try to model a self-scheduling problem for the any renewable power uh, company. Okay, and like very detailed like formulation we will look at. If you have any doubts, please ask. If you don't have any doubts, I can quickly complete value of stochastic solution as well. I will, it's hardly take 2 or 3 4 minutes, so we can go above time 2 3 minutes. So let's see. Let's look at the VSS, value of stochastic solution. So it is basically again for different objectives. Like if we have a maximization objective, the value of stochastic solution is basically whatever is our stochastic solution minus whatever is the deterministic solution. So we will take a difference of our stochastic solution and deterministic one, and for VSS min, it will be Z D conjugate minus sorry optimal minus Z stochastic optimal. This star is not conjugated; it is basically for optimal value. Okay, so higher value of VSS indicates that it is basically considering uncertainty in critical for making decisions. So if it is higher value, um, you should consider uncertainty for making a decision. If it is less, then the difference between the stochastic solution and deterministic solution is not much. So you can let go of uncertainty and don't worry about uncertainty because the difference is very less. If this difference is very much high, uncertainty is affecting our solution as compared to the deterministic one. So if it is low, uncertainty is not basically affecting our objective, then we can easily say that okay, there is no need to consider uncertainty because the difference is very low and it will not make much difference in our objective function. So if I again go back, like one consider example. So one example we will consider. Okay, so first of all, let's consider the same example. If I take a average demand, so average demand will be we have 20% of chance of 110, then 60% chance of 100 in the very first example, and then again 20% chance of 80 megawatt. So this is 98 megawatt hour demand was there for a particular hour. If I talk about average price to procure this demand, it is again 0.2 into there was first price was 50 plus 0.6 into 46 plus 0.2 into 44. 45 was the Pareto price. So the price will be average price is $46.4 per megawatt hour. That is the price. So if this for this particular like average price and average demand, I can put an objective function. 168 is the hour, and bilateral prices were fixed. So this is PC plus uh, price average price is 46.4, and this will be the quantity in pool, and subject to we will have a PC plus P, and instead of like 110 demand, we will put it at the average demand, that this is the average demand. So the PC should be 90 and 0, and P should be positive. The solution for this particular problem, if you simply look at it, is very straight away, that this price is higher, this is low. So PC will be equals to 90. So this is what the decision will look like. Then I will solve with this particular value. I will solve the values of P1 and P2 and P3. So if it is known, I will again minimize, and I will get a deterministic solution now. So CD will be equals to that. Uh, Bilateral contacts are fine. So this we will assume that it is fixed. So this is called our deterministic solution, and this is 45, and this PC is now determined. So this is fixed, and we are not keeping it as a variable. Then I will put 0.2 into 50 into P1 uh, plus 0.6 into 46 into P2 plus 0.2 into 44 and multiplied with P3. So this will be my objective function. Subject to constant, this PCD is already defined. So I can say P1 should be more than equals to 110 minus PCD. Okay, so I will reduce this one, that it is already defined. P2 will be 100 minus PCD, and P3 will be 80 minus PCD. Okay, once it has been defined, another part is like all these P1, P2 and P3 are positive variables. So the solution of this particular problem is P1 equals to 20, P2 equals to 10, and P3 equals to 0. So it is a deterministic solution. You can solve them like parallel as well, because nothing is coupling them. And the CD optimal value will come equals to, like if I put these values here, 760 and 368. In this case, the value of SS min will come equals to whatever we had earlier, basically like deterministic minus value of stochastic star. So this is what I think we have defined here as well. So for min, whatever is the deterministic solution minus stochastic solution. So here the deterministic solution was 760368 minus earlier the stochastic solution was 47936, and this value was coming equals to 124. It is again dollars and 32. So this is VSS min. You can also solve these values for our three-stage problem for the generator. The same example. If it is so for two stage, it is fine that it is a difference between the two stage. For three stage, first of all, we have to calculate, let's say, expected value of PI. Um, 1. Okay, and then we will calculate the expected value of PI between second and third stage. That will be equals to basically the total expected value of perfect information. Similarly, we will calculate expected value of stochastic solution of between first and second stage, then value of stochastic solution in the second stage. That will be the overall total value of stochastic solution, and you can basically add on the multiple stages. If it is 4 stage, you have to calculate the 3 times these values. Okay, so this is how we can solve it. So I think this is all from my side. In the afternoon 2 to 4, we will talk about the how we can model the renewable self scheduling and how we can solve it. So thank you. Thank you.